Like you all to learn these sums that I am teaching you now, the basic sums using refractive index. First of all, to do sums using refractive index, you should understand Snell's law. This is something that you studied in 10th standard, Snell's law. It states that the refractive index is equal to sin I by sin R, which I already taught in the class. Refractive index, that is when the light ray is entering from rarer into a denser medium, we say mu is equal to sin I by sin R. Okay, where refractive index is always with denser medium with regard to rarer medium in my terms. So mu is equal to sin I by sin R. You should also know that same refractive index can also be written as velocity of light in vacuum by velocity of light in the medium. Okay, so refractive index can also be written as, velocity is distance by time, which is distance becomes wavelength and 1 by t becomes a frequency. So velocity is also lambda into frequency. So substituting here for this c, which is velocity of light, c is nothing but the velocity of light in vacuum. So it's lambda in vacuum into frequency in vacuum by lambda in medium, because V here stands for velocity in medium. So lambda in medium into frequency in medium. The frequency in vacuum and medium does not change. During the process of refraction, the frequency is unaffected because energy does not change. Only the speed changes, and speed is dependent only on the wavelength. This is something you need to know. The speed is only dependent only on the wavelength and not on the frequency. So these are the formulas you should know about Snell's law. What are those? A refractive index is equal to sin I by sin R when light is entering from rarer to denser. The refractive index is also velocity of light in vacuum by velocity of light in the medium. The refractive index is also, that explains, this point here explains that velocity of light in vacuum will be faster than the velocity of light in the medium. So then the answer will always be greater than 1. That explains why a refractive index is always greater than or equal to 1. Because numerator has got vacuum where the speed will be larger. Then the refractive index is also wavelength in vacuum by wavelength in medium. So these are the three formulas you should be really clear with. And the frequency remains unchanged whether it's in air or in any other medium. Okay, in vacuum or any other medium. So let's talk about this sum, which is example 13. Okay, a ray of light with frequency 5 into 10 to the power 14 hertz is passed through a liquid. The wavelength of the light in the liquid, in the medium. The liquid means in the medium has been given to be 450 into 10 to the power minus 9 meter. Calculate the refractive index of the liquid. Refractive index of the medium, basically. And you know the formula for refractive index of the medium. With regard to wavelength, wavelength in vacuum by wavelength in medium. And do you know the wavelength in vacuum? Wavelength in vacuum, velocity is distance by time. So velocity is lambda into mu. From here, So you have the frequency which is in air and in also medium. Okay. So then therefore with which lambda can be found, which is c by mu. Because I am going to talk about vacuum only here. You can use the frequency in vacuum and the speed in vacuum, which will give you a wavelength in vacuum. Okay, wavelength in vacuum is 3 into 10 to the power 8 by the frequency 5 into 10 to the power 14 hertz will give you the wavelength in vacuum. Once you get this value, you can bring it in here and substitute to find the refractive index of the medium, which is a wavelength in vacuum, which is 3 into 10 to the power 8 by 5 into 10 to the power 14 into denominator, which is wavelength in medium, which is 450 into 10 to the power minus 9. On solving this, you'll get 1.33, which shows that this is water. This liquid happens to be water. You all know that. Okay, so that's how you do the sum. Next is example 14. Example 14, you have a refractive index of glass with respect to air, obviously, 3 by 2. A refractive index of water, again with respect to air, which is 4 by 3. The speed of the light in glass. The speed of the light in glass is 2 into 10 to the power 8 meter per second. What is the speed of light in water? And refractive index, and then the speed of light in glass has been given, speed of light in water has been asked. You have refractive index of, let's assume that it's entering from water into glass. Let's assume that is the light ray is entering from water into glass. So that the refractive index will be glass with respect to water, because my light ray is entering from rarer to denser. which is mu of glass by mu of water, both of them with respect to air, which will be equal to, what is mu of glass? Refractive index in glass, the speed of light in vacuum by speed of light in glass, by refractive index of water, speed of light in water by velocity of light in water. C and C get cancelled. So V of water and V of glass. So then therefore, mu of glass with respect to air is 3 by 2, mu of water with respect to air is 4 by 3, which is equal to velocity of light in water by velocity of light in glass. So then this becomes 9 by 8 into 2 into 10 to the power 8, which will give you velocity in water. The value itself is 2.25 into 10 to the power 8 meter per second. Let's go to next sum. Example 15 in Aurora. The wavelength of the light is 4500 Armstrong, which means it's 4500 into 10 to the power minus 10 meters. A light in vacuum enters a glass block. From vacuum, it's entering into glass, which means from air to glass basically. The glass refractive index is given to be 1.5, which is glass with respect to air therefore. And what is the frequency and wavelength of the light in glass? Do you know that the frequency whether in vacuum or in glass will never change? I told you that the frequency remains unchanged during refraction. So the frequency can be calculated in air, which will also be the frequency in glass, doesn't change. So therefore mu is equal to C by lambda, where we can take a C to be the velocity of light in vacuum by the wavelength in vacuum itself. Yeah, because the wavelength frequency does not change, so you can see what is it in air and you can write the same thing in glass. So 3 into 10 to the power 8 by 4500 into 10 to the power minus 10 will give you the frequency, general frequency, whether it's air or glass, it's the same. So this value is 1 by 15 into 10 to the power 16 hertz is the frequency. So calculating the frequency was very easy. We calculated it for air and we are saying that it's going to be the same whether it's air or glass. But the question is, what is the wavelength in glass? The refractive index in glass is nothing but speed of light in glass by the speed of light in vacuum by speed of light in glass. Okay, and the question is, what is the wavelength of light in glass block? Okay, you know the direct formula with regard to wavelength. The refractive index is also equal to the wavelength of the light in vacuum by wavelength of the light in medium, which is a glass, air and glass for example. And the wavelength of the light in air is the given wavelength, which is 4500 into 10 to the power minus 10 by the wavelength in glass is what you don't know. Hence the refractive index of the glass with respect to air is 1.5. Just cross multiplying 4500 10 to the power minus 10 by 1.5 will give you wavelength of the light in glass, which is 3000 Armstrong. Okay, this is another sum. Let's go to example. Now let me do example 17. I'm not doing every sum, I'm doing only the important sum. There's a container which consists of water, a trough which consists of water. There's a rectangular glass slab placed at the bottom of it. A ray of light is incident on the water surface from outside at an angle of 50 degree. So then there's a ray of light which comes and falls in here. At this point of incidence, as you know, I have to do a normal. And this angle they've given it to be a 50 degree. And the light ray is entering from air into glass, so it's going to bend towards a normal. And it's going to fall on the glass, where again at this point of incidence I have to do a normal. And the light ray is going to bend towards a normal. And this angle is what they're asking. This R dash is what they're asking. For which you should know this angle. For which you should know this angle. This is a Z angle, interior alternate angle. So if I know this angle, I'm sorted. This X and this X. So let's go to this space. Refractive index of this is water. It's 1.33 with respect to air, which is equal to sine 50, which is sine I, by sine R, which is sine X. So refractive index of water is 1.33 is equal to sine 50 by sine X, and cross multiplying. You will get what is your sine X. Sine X therefore is sine 50 by 1.33. And 1.33 is also 4 by 3. Okay, so that's you get a sine X. Once you get a sine X, you go to this surface here, glass surface, sorry. Go to this surface where you have a glass with respect to water, because light ray is entering from water into glass at this phase, which will be mu of glass by mu of water, both of them with respect to air. Mu of glass is 1.55, mu of water is 1.33, which is equal to sine I by sine R, which is sine X by sine R dash. This is the angle of incidence, it's the angle of refraction in this phase. And you would have found sin x from here, you can substitute and hence find sin r dash. Is very simple. Of course, the calculation will you'll not be able to do it because we don't know what is sin 50. If given, then we can do it. Okay, otherwise we can't do these sums, but just generally going to know how to do these sums is very, very critical. So then example 18. The rectangular side, okay, this is about a glass slab of thickness 6 cm is made up of refractive index √3. When the light is incident on one of the parallel faces at an angle of 60 degree, it emerges out of the parallel face. Find the lateral shift of, the lateral shift is nothing but d, and you all know the formula, sin I minus r by cos r into thickness. And okay, the glass slab experiment, if you all remember, there is an incident ray here and there is a normal at the point of incidence. The light ray is going to bend towards the normal, and again at this point you have to have one more normal, and is going to bend away from the normal here. You all know this, and this is your I, this is your R, and this light ray would have gone like this if there was no glass slab, and this is known as lateral displacement. And you remember I used to mark this as a cross here and mark this therefore as I minus R. Very, very critical. And the formula of sin I minus R is this angle. They have given this angle of incidence to be 60 degree. The angle of incidence to be 60 degree. Nice. You need to know what is R so that you can find sin I minus R. So then take this phase, which is the refractive index of glass with respect to air, which is sin 60 by sin R. And the refractive index of glass, you know, is 1.5, is sin 60. And what is sin 60's value is √3 by 2. Can we write 1.5 as 3 by 2 for convenience, is equal to sin 60, which is √3 by 2 by sin R. 2 and 2 get cancelled. So this and this gets cancelled. I get a 1 by √3, is it? I get a √3. And so sin R becomes 1 by √3. And sin R becomes, something is not okay. Let me do it again. Take the same phase where you have refractive index of glass with respect to air, which is sin 60 by sin R. The refractive index of glass, they have given the refractive index of glass to be √3. Okay, so don't take it as 1.33. They have given in the sum it's √3. So then sin 60 is √3 by 2 by sin R. So √3 get cancelled. Sin R is equal to therefore 1 by 2. Where will sin R be 1 by 2? When R is equal to 30 degree. Therefore you know this is 30 degree. This is 60, and therefore sin I minus R is 30 degree. So sin 30 by cos R is also cos 30 into thickness of the glass slab, which is given in the question to be 6 cm. So 6 into 10 to the power minus 2. This is tan 30 into 6 into 10 to the power minus 2. What is tan 30's value? Tan 30 is 1 by √3 into 6 into 10 to the power minus 2. So that will give you your answer. It is they have given here in centimeter, but okay, you can also keep it in centimeter if you want to keep it in centimeter. And you can write the answer as 3.564 centimeter. And if it's meters, into 10 to the power minus 2. So then I hope you understood. The finding the I minus R was tricky. Okay, so you have to know the concept to be, if just remembering the formula is not going to help you. To find the R is like very critical, and then finding sin I minus R. Okay, let's go to the next question. The next question that we'd like to do is example 20, where the velocity of light in glass is 2 into 10 to the power 8 meter per second. The velocity of light in air is 3 into 10 to the power 8, which we have know is vacuum, right? By how much would an ink dot appear to be raised when covered by the glass plate of 6 cm thickness? An ink dot and a 6 cm thickness is the height, the actual depth, which means. So the question is, how much will it be raised? They are asking about how much will it be raised. Are they asking about apparent depth or shift? I think then they are talking about shift. How much will it be raised means it's shift. Apparent depth means it's this, right? The light ray which is coming here is going to bend away from the normal. It's going to appear to come from point, and this is the apparent depth, and this is the shift, as you all know. And the question is about the shift. You all know the formula for shift itself directly. It's d into 1 minus 1 by mu. D itself is 6 centimeter into 1 minus 1 by mu, where refractive index of the glass. But they haven't given the refractive index of the glass. We know it's 1.5. Whether we are allowed to take it, I don't know. So then just do refractive index of the glass with respect to air. Can also be a velocity of light in vacuum by velocity of light in glass, which is 3 into 10 to the power 8 by 2 into 10 to the power 8. We're using the given values, let's find it. So it's 1.5 and that's exactly what it is, but you need to use what is given. So 1 minus 1.5 and you all know 1.5 is 3 by 2, so it will become 2 by 3. So 6 into 1 by 3, so it's 2. That will be the shift, 2 centimeter. But I'm keeping centimeters as centimeters in this, and I can always say 2 into 10 to the power minus 2 meters after the calculation. Okay, that's a very nice sum. So you must learn all these sums. So let's go to example 23. It's a very nice sum, but it's never been asked in any exams. But I always teach this sum, which is very interesting to learn. A transparent cube of 15 centimeter edge containing a small air bubble. Okay, so there's a transparent cube. You know how to draw a cube in which you have some air bubble. The apparent depth when viewed through one face is 6 centimeter, which means it's appearing to be 6 centimeter from one of the faces. See, let's say I'm looking at it through this face, okay? My eye is here. The apparent depth is found to be 6 centimeter. This is the apparent depth, 6 centimeter apparent depth. Okay, the transparent cube, 15 centimeter is the total. Okay, this is 15 centimeter, okay? I'm getting to see an apparent depth 6 centimeter. I don't know what is actually. When viewed through the opposite faces, oh, the apparent depth through this face is again given to be 4 centimeter. And 6 plus 4 is 10, so the gap between them obviously is 5 centimeter. Correct? Okay. So then I don't know where the object is. Can I consider the object is here then? Somewhere here. Where at a distance of x here and so at a distance of 15 minus x here is the distance of the object. This is the distance of the image. The purple color, the red color is the distance of the image. The x and 15 minus x happens to be the distance of the object. And let's do, you know, it's nothing but a glass slab which has got, it's glass and the refractive index of it, can I take it as 1 by, okay. What is the question? Find the refractive index of the material of the cube. You can't write it as 1.5. The whole objective is to find the refractive index to be 1.5. And you know the refractive index we want to find is actual depth by apparent depth. Let's look at this face. And the refractive index is what is the actual depth? You don't know, you're considering it as x. But the apparent depth at that face is 6 centimeter. So let's look at this face. The refractive index is actual depth, which is 15 minus x, by the apparent depth, which is 4. But you know that both the refractive index are the same. It's the same material. So x by 6 is equal to 15 minus x by 4. So then therefore a 4x is equal to 15 6 are 90 minus 6 6. So a 10x is equal to 90 and x is equal to 9. Therefore you understand that from here it is 9 centimeter the actual position of the object, and therefore from here it's 15 minus 9 which is 6 from the other side. And you now know the actual depth. You can take it and substitute it here to find the refractive index, which is 9 by 6 or 3 by 2, which is 1.5, which is obviously the refractive index of glass slab. We are not supposed to write that. We are supposed to do the sum in actual and find the answer. I hope you are all clear. It's very, very important. These are the important sums with regard to refractive index and lateral displacement and real depth and actual depth and real depth by apparent depth or actual depth by apparent depth, those kinds of concepts. So let's go to example 25. The value of the critical angle of the material of refractive index, root 3. Okay, they've already given root 3 to be the refractive index. They're asking critical angle, and you all know sin IC is equal to sin inverse of 1 by mu. IC is equal to sin inverse of 1 by root 3. And 1 by root 3 will be in which sine angle? Sine of 30 is 1 by root 3. So it is a 30 degree, which is 1 by root 3. Okay, but the question is about mu has been given. A question is about critical angle. So can I say 1 by root 3 will come? No, something is not alright. Okay, the value of the critical angle of the material of the mu is equal to root 3. Sine, where will I get 1 by root 3? Sine, I don't get 1 by root 3. Now, my angle, sine is always 1 by 2. Sine 30 is 1 by 2. Or sine 60 is root 3 by 2. I don't get a 1 by root 3. So, how do I find it? Okay. So, sine inverse of 1 by root 3 into root 3 by root 3 is anyway mu is equal to sine inverse of root 3 by 3. Anyway, we don't know this. Okay, we cannot find out unless it's given. The Clark's table is given, unless they give you the value, we cannot find out. You can write it like this, and this is the refractive index. Leave it like that. Actually speaking, IC is equal to sine inverse of 1 by mu. IC is equal to sine inverse of 1 by root 3. We do not have 1 by root 3 as any sine angle, so I'm sorry. Therefore, you can leave it like this, and this is how you find the critical angle. Leave it like that. Okay. They are using the Clark's table and finding it to be 35.3 degree. We can't obviously find out because unless Clark's table will not be given in the question. So example 26. The speed of light in medium is to be calculated. The critical angle has been given. IC is 30 degree. And you all know IC is equal to sine inverse of 1 by mu. So IC itself is 30 degree is equal to sine inverse of 1 by mu. Therefore, sine 30 itself is 1 by mu. And sine 30 is nothing but 1 by 2. So mu is equal to 2. Therefore, we are getting the refractive index of the medium to be 2. So, and you know refractive index is equal to velocity of light in vacuum by velocity of light in medium. If this is going to be 2, this is 3 into 10 to the power 8. Hence, you can find the velocity of medium, which is 3 by 2 into 10 to the power 8, which is 1.5 into 10 to the power 8 meter per second. I hope you all understood such a beautiful sum using critical angle. Small 1 mark questions. Okay, please understand and do these sums because these are 1 mark questions which repeatedly are asked in board exams. So the next sum which has come in board exam is example 28. In the following ray diagram, calculate the speed of light in the liquid of unknown refractive index. So they have given a beaker, there is a liquid, the ray is actually coming from here and grazing through the surface, which means there's a normal here, this has to be critical angle. Okay, they have given this to be 40 centimeter. They have given this to be, it's 30 centimeter. And moment this is 30 and 40, you can find, can you take this triangle and you can find a tan IC. A tan IC is opposite, which can also be 30 by adjacent, which is 40, which is 3 by 4. So, but you only need a sine IC to find the refractive index, and so you can do a triangle, right? 3 here, a 4 here, and so this is a triplet, is it? Yeah. So this is 5 here, and therefore a sine IC itself is nothing but a 3 by 5. Therefore, IC is equal to sine inverse of 3 by 5, and you know the refractive, it's nothing but IC is equal to sine inverse of 1 by mu. Yeah, hence we can find the refractive index of this. This 3 by 5 can be plugged in here as 1 by 5 by 3. Isn't it? And hence we know that the refractive index of this has to be 5 by 3. What is 5 by 3? It's 3 ones are 3 and a 20. 6 threes are 18. 26 threes are 18. And I'll get the refractive index of the medium. So that happens to be some 1.6. Okay, so or you can keep it as 5 by 3. That's the refractive index of the liquid. But what is the question? Find the speed of light inside the liquid. Speed of light inside the liquid with respect to air is refractive index, which is nothing but speed of light in vacuum by speed of light in medium. This itself is 5 by 3. This is 3 into 10 to the power 8 by velocity in medium. So then therefore velocity in medium is 9 into 10 to the power 8 by 5. So 5 ones are 5, 8 fives are 40 into 10 to the power 8 meter per second will be the velocity of light in the liquid. Very, very beautiful sum. This diagram will be given from which you know if it's grazing through the surface, it means this has to be critical angle. And to find the critical angle, you have opposite and adjacent. So you can find tan IC, from which you can find sine IC, from which you can find a mu, and then from mu you can find the velocity of light in the medium. So let's go to the next question. This is again a CBSE question, which is example 29. Example 29. Calculate the critical angle for a glass air surface. The ray of light which is incident in air on the glass surface is deviated through 15 degree. The angle of incidence is 45 degree. The angle of incidence is 45 degree. Okay, it's a very tricky sum. It's a very tricky sum. I won't say this is coming, but it will come for PSC now, I'm telling you. Calculate the critical angle. Means IC is equal to sin inverse 1 by mu, correct? Okay, for a glass air interface. So you have a glass and you have an air interface. If a ray of light which is incident in air, which means it's in air, it's coming from glass. Is it? Quite tricky question, I don't understand. If the ray of light which is incident in air on the glass surface is deviated through 15 degree. See, let's understand this question, okay? Okay, so which means it's entering only from air to glass. Air to glass. Read the question again. I'm reading it. The calculate critical angle for the glass air interface, the ray of light which is incident in air on the glass surface is deviated through 15 degree. Deviation is 15 degree. Okay, which means a light ray is coming like this and falling on this. You have to have a normal here. It's going to bend towards a normal because, but the question is about the deviation. Deviation means this ray would have gone like this, but it's deviated like this. This is the question. It's not about the angle of refraction, it's about the deviation. Deviation from its original path. That's where it's tricky. Okay, and they have given that it's deviated through 15 degree. Oh, it's deviated through 15 degree. This has been given. Deviation is 15 degree. And you know this is R, angle of refraction, and this is I, and they have given that angle of incidence is 45 degree. And you remember I used to put this red cross mark and say that this is equal to this. So 45 is equal to R plus 15. So R is equal to 30 degree. So therefore you get R to be 30 degree. Once you get R, you can find the refractive index. So refractive index of glass with respect to air is nothing but sin I by sin R, which is sin 45 by sin 30. I like these sums because angles are clear, easy to find out. 1 by root 2 and sin 30 is 1 by 2. So it will become root 2. The refractive index of glass to air itself is root 2. And you know, to find the critical angle is sin inverse of 1 by mu, which is sin inverse of 1 by root 2, and therefore IC is equal to pi by 4 or 45 degree. So beautiful sum. Okay, so let's go to the next question, which is example 31. A ray of light falling normally on the face AB of an equilateral prism having refractive index as 3 by 2. Okay, a prism is having a refractive index of 3 by 2. A ray of light is incident normally. Okay, so let's draw a prism. A ray of light is coming normally like this, which will go undeviated like this. It will go undeviated, correct? It's falling on the face AB of refractive index 3 by 2, which is refractive index glass with respect to air is 3 by 2. Oh, placed in water. Oh, you're going to place it inside water. You're going to place this entire thing in water now. And the light ray is entering normally. Okay, glass or refractive index is given to be 3 by 2, which is generally only with respect to air. And they've also given that placed in water of refractive index 4 by 3. Refractive index of water with respect to air is 4 by 3. Will the rays suffer total internal reflection on this face AC? If it has to undergo total internal reflection, it has to be, angle of incidence has to be greater than the critical angle. So let's do a normal here. This has to be greater than the critical angle. So let's find out what is the critical angle here. The light ray here is entering from water into glass. Obviously it's entering from water into glass. So mu of glass with respect to water is all you need. Okay, and mu of glass with respect to water is mu of glass by mu of water, both of them with respect to air. So mu of glass with respect to water is 3 by 2, water with respect to air is 4 by 3. So it's 9 by 8 is mu of glass with respect to water. And if you want to find the critical angle, and the critical angle is sine inverse of 1 by mu of glass with respect to water, which will be IC is equal to sine inverse of 1 by 9 by 8, which will be sine inverse of 8 by 9. Okay, you get something like this. So then therefore you get IC is equal to sine inverse of 8 by 9, which is therefore sine IC is equal to 8 by 9, whose value is 0.89 approximately. So this is your sine IC. Okay, this is your critical angle. But what is the angle of incidence at which it's falling? Let's see. Shows a ray of light falling on the face. Equilateral glass prism shows that this is 60 degree. Therefore, you know this is 60 degree. You know this is 90 degree. And therefore, this has got to be a 30 degree. And therefore, you know this normal, this is already 60 degree. This is your angle of incidence. So, sine 60 is your angle of, it's your incident angle on that face. Sine 60's value itself is root 3 by 2. And here the critical angle is sine IC, okay, which is 8 by 9, which is 0.89. What is root 3? 1.732 by 2, which is 0.8. 6 and 6. And can you see which is bigger, the incident angle or critical angle? 0.86. The critical angle is greater than the incident angle. For total internal reflection, the incident angle should be greater than the critical angle. It's not. So this ray would obviously get refracted. This ray would obviously get refracted, move away from the normal, and I have to complete this diagram like this. And this comparison, and I hope you all understood, it's very, very important sum. So let's go to the next question. The next question is this example 34. Example 34. A point source of light S is placed at the bottom of the vessel containing the liquid of refractive index 5 by 3. Take a vessel. It's got a liquid of refractive index 5 by 3, which is a refractive index of liquid with respect to air, obviously. A person is viewing the source from the above surface. Okay, there is a source of light inside this. And you know, from the source, the light ray will go like a cone only. You should know this. So that it can have a normal here, and it is the critical angle, then it will graze through the separation. If this is the critical angle here also, it's a critical angle here, it will graze through the separation. Very important to know to draw this, okay? Otherwise you can never do this sum. A person is viewing the source from the above surface. There is an opaque disc of radius 1 centimeter. Yeah, obviously, can you see? This will be an opaque disc. Okay, which is being placed here, of size of radius 1 centimeter, floating on the surface. Somebody is viewing it from outside. There is a disc which is placed on the circular portion, so which means you cannot see the light through that circular portion. Okay, there is an opaque disc of radius 1 centimeter floating on the surface. The center O of the disc lies vertically above the source. Yes, the liquid from the vessel is gradually drained out through a tap. It's an IIT question. Okay, the liquid is going to be drained out through a tap. What is the maximum height of the liquid for which the source cannot be seen at all? Okay, let's do the sum. Okay, people, this will never come for your school exam, but it's better to learn something. IIT sum has been given, and you know sine IC. Let's consider the point of incidence as A here, and sine IC is equal to opposite, which is the radius, by the hypotenuse. And if you assume the height of the water to be h and this is 1 centimeter to be radius, it is root of h square plus r square. The root of h square plus r square, which is the hypotenuse. So you write a sine IC, and you all know sine IC is also 1 by mu. Therefore, mu is equal to root of h square plus r square by r. Okay, so then you can square both sides, so you get mu square is equal to h square plus r square by r square. squaring both sides, because with the root it's hard to find the answer. So then now what you do is cross multiply mu square into r square is equal to h square plus r square. Consolidate r square into mu square minus 1 is equal to h square. So with this, you can take a square root, and it is mu square minus 1 is equal to h. So we can therefore find what should be your h. You know the radius is just 1. Refractive index is given to be 5 by 3 the whole square minus 1, which will give you your height h. So then the answer for this is given to be 4 by 3 or 1.33 centimeter. So the liquid from the vessel is gradually drained out through a tap. What is the maximum height of the liquid for which the source cannot be seen at all? So beyond the point, when you drain out, actually when you drain out the water, the disc will also go lower, right? And once again, hold on. See, basically you cannot see the source. You cannot see the source. The rays are not coming out. The rays are not coming out. You cannot see the source from outside. So then therefore, when the rays will not come out, only when it undergoes total internal reflection. So for total internal reflection, you know that using the refractive index, you're finding what should be the height. And so at the height of, till the height of 1.33 centimeter is when you will be able to get to see the, at this height the total internal reflection phenomenon occur, you will not be able to get to see the source. That's the question. It's quite a complicated one, but I hope you all understood. Okay, so that is about it, guys. If you can practice these sums, this is the first set of sums that I would like you, apart from the book bag that I did, this is the first set of extra questions that I would like you to learn. Okay, the first video.